Hello everybody, let me start lecture 61 and the course is on phase diagrams in single component and binary systems. The topic for discussion is on peritectic phase diagram, and we will also try to see one or two examples of bit complicated phase diagram and try to relate it with free energy composition diagram. If you see last class, we have actually analyzed iron carbon phase diagram, and we have seen there are three reactions: peritectic, eutectic and eutectoid. And this is a metastable phase diagram because it talks about iron and Fe3C. These two are the main components, and it extends till 6.67 weight percent carbon, because your Fe3C has carbon content around 6.6 weight percent. Now, coming to two major reactions, one is eutectic and eutectoid we have analyzed, but another major reaction that happens at a little higher temperature around 1490 around that degree Celsius, around that temperature, and there one solid reacts with another liquid, forms a different solid. Okay. So, that is the peritectic reaction, and we will try to look at that reaction and try to relate it with free energy composition diagram and check how different phases appear at a particular temperature. And how do we do that? We try to see free energy hierarchy as well as we check common tangent rule. In fact, we will always keep the pressure at 1 atmosphere. Now, let us start. We have actually checked the iron carbon metastable phase diagram, or I can say iron Fe3C phase diagram. Fine. We will plot y axis, we will plot temperature, x axis is percentage of carbon, which is in weight percent, and the phase diagram looks typically like this. This is 6.67% weight percent carbon. This is iron rich, this is iron, 100% iron, and the plot is like this. Okay, this one should be starting from here. Fine. Now, if I quickly put all the values, temperature, this is temperature axis, this is composition. These are all carbon content. This is 2%, 4.3%, this is 0.8%, this part is 0.025%. Okay. And the phases are, here we have delta, delta plus liquid, this is liquid, gamma plus liquid. In this zone we have delta plus gamma, gamma. Here we have alpha, alpha plus gamma, gamma plus Fe3C, liquid plus Fe3C, and here we have alpha plus Fe3C. Okay, all the points are marked and all the phase boundaries are also marked. We have this is eutectoid point, and two more temperatures we have to follow it up. It is 1147 degrees Celsius, and this is 727 degrees Celsius, around that. Okay. This is eutectoid point. This point is eutectic, and this particular point is peritectic. Fine. And we have already done eutectoid and eutectic point. Now, at eutectic point, at peritectic point, we have delta plus liquid, it is going to gamma, and delta is BCC, gamma is FCC. These are the two crystal structures of delta and gamma. Now, we have to see with reference to peritectic point, that particular area, that particular zone, we have to see what is the free energy composition diagram. For that, we will take a generic consideration, considering binary solution of metal A and B, okay, and they have composition X A and X B. These are the mole fraction, would be equal to 1 mole. We are talking about 1 mole solution, and temperature and pressure is kept 1 atmosphere, and each temperature we will be trying to see equilibrium conditions, and that information will be taken to temperature composition plot. Now, if I look at the peritectic generic diagram, that looks like this. This is for XB 100% or XB equal to 1, and this is XA equal to 1, fine, two extreme ends. And now, we can consider this is to be TMB, and let us say this is TMA, as we have been considering that melting point of metal B is higher than melting point of A. That is what I have placed melting point of B on the higher end. Now, I can see the phase diagram would be, I can put this particular temperature little at the higher point. Okay, so this is liquid, this is delta plus liquid, gamma plus liquid, this is gamma, this is delta plus gamma. This is the phase diagram of typical peritectic transformation, and this is the point what is basically peritectic point. Now, if I try to look at, this is TMB and this point is TMA. Now, if I try to see at different temperatures the free energy composition diagram, so I will mark those temperatures. So, one temperature let me take here, another temperature, this is T1, another temperature which is equal to TMB, then one more temperature we are consider in between just below TMB, this temperature which is let us say T2. One temperature we will consider at T peritectic. One temperature I can consider here, which is T3. Then one is at this is T4. One more is at T equal to TMA, and then I will go farther down, which is T5. So, if I try to check the free energy composition diagram starting with T1, let us see how it looks. This is XB, fine. So, let us say this is for delta or G2 delta, this one is for G2 gamma, and this is for G2 liquid. This is T equal to T1, and this is the free energy composition diagram. You see over the entire compositions liquid is stable, and here also on the phase diagram also you can see at T equal to T1 everything is liquid. Now, I will see at T equal to TMB. T equal this is XB. Now, here I will see a situation like this. This is G2 gamma, this is G2 delta, this is G2 liquid, and at T equal to this is T equal to TMB. I could see that the delta will have equal free energy with liquid at when it is pure B. So, the first point will appear here. Okay. Now, if I take at T2, T equal to T2, this is G2 liquid, and we have G2 delta and we have G2 gamma. This G2 gamma could be, I can draw it like this. Please understand that G2 gamma is still above G liquid, G2 liquid, and G2 delta and G2 liquid, they are now they are going to have a common tangent. So, the common tangent, if I draw, this is the common tangent. So, this composition and this composition, they are under equilibrium. These are the two phases that will coexist at T equal to T2. So, this is XB of delta, XB of liquid in equilibrium with delta. This is XB of delta in equilibrium with liquid. So, these two compositions are marked here. One is at this location, another one is at this location. So, this is XB liquid delta and this point is XB delta liquid. Now, if I do it at T equal to, this is G, T equal to T P, which is peritectic temperature. So, I will have a plot like this. So, this is the liquid one, this is the liquid one, G2 of liquid. Please understand that G2 is always the free energy of the solution. So, we know that G2 equal to G1 plus delta J mix, and G2 is the solution free energy, G1 is the unmixed free energy of the system, and delta J mix is basically the free energy of mixing when these two components are mixed at different compositions. Now, this is the one, and then we can have a situation like this. So, this is the delta, and we have now one phase which will be, that is basically the gamma phase. So, gamma phase, let me just do it, let me just draw a common tangent first, and the gamma phase will actually go through this. So, this is the gamma phase which is coming up. Now, here this composition is X P or X P of gamma in equilibrium with liquid and delta. This is X B of delta in equilibrium with gamma and liquid, and this one, this particular composition is X B of liquid in equilibrium with gamma and delta. Now, these 3 points are marked here. So, this is one point, this is another, and this is another. So, this composition, this is the composition, this is X B of gamma in equilibrium with liquid in equilibrium with delta. This one is X B of delta in equilibrium with gamma and liquid, and this one is X B liquid in equilibrium with gamma and delta. Now, here I could see that delta plus liquid actually having an equilibrium with gamma. So, this is nothing but peritectic reaction. This is nothing but peritectic reaction, fine. So, these compositions are marked there. Now, this is G, this is T equal to T P, which is exactly matching with the peritectic temperature, and this composition is nothing but peritectic composition X P, and this temperature is T P. Now, if I do it at this is X P, X P equal to 1, X P equal to 0, and now at T equal to T3, we will have a typical plot like this. So, now this is gamma line, G2 gamma. We have delta on the right side, okay, and then we have liquid on the left side. Okay. So, this is G2 liquid, this is G2 delta. Okay. Now, I can see the common tangent now. Here in case of T equal to T P, the common tangent was here, which is passing through all 3 free energy composition plots, but here we will have 2 common tangent, this is one, another one is this one. So, we have composition 4 compositions, okay. So, these compositions can be marked as Xb of liquid in equilibrium with gamma. This is Xb of gamma in equilibrium with liquid. This is Xb of gamma in equilibrium with delta. This is Xb delta in equilibrium with gamma. And these 4 compositions are marked here. So, this is one, this is another, this is another, this is another. And I can actually write that this composition is Xb liquid in equilibrium with gamma. This is Xb gamma in equilibrium with liquid. This one is Xb gamma in equilibrium with delta, and this one is Xb delta in equilibrium with gamma. And here the temperature is T3, which is below Tp, and this is free energy. Now, if I try to look at T equal to Tp, or rather if I look at T equal to T2, left to this I see all liquid and right to this I see all delta. In between we have liquid plus delta. Exactly we have that situation, that truncated I region is actually having delta plus liquid. Whereas, in case of Tp, T equal to Tp, we see left to this particular composition we have liquid, in between, rather this is the region between this two liquid composition and delta composition, we have existence of liquid plus gamma plus delta of those compositions only. Right to this we have delta. Okay. So, like that way we demarcate those phases, and those are appearing, for example, those are appearing considering common tangent rule and free energy hierarchy rule. For example, left to G, or in this case left to this G, B, liquid, gamma, delta, we see liquid has lowest free energy, and that is where liquid would be stable. Exactly we see that situation on the phase diagram, and accordingly you can decide at T2 what will be the phase boundaries and phase regions. Fine. In fact, now we have this, between these two we have gamma, and here we have gamma plus delta, and in this zone we have liquid plus gamma, and here we have liquid, and on this right side we have delta. Exactly same phases are appearing there. Now, if I do it at T equal to T4, the free energy composition diagram, this is Xb, fine. Now, here we see that the liquid line will still exist. Liquid line would be here. Now, delta actually will vanish, because at T4 we do not have any delta region. So, the T4, the delta will move up, and the gamma will have its position here. Liquid, I can do it little on the like this, and gamma would be like this. This is G2 gamma, this is G2 delta, and this is G2 liquid, and we can have a common tangent here also. So, these two are the composition Xb liquid in equilibrium with gamma, Xb of gamma in equilibrium with liquid, and those two compositions are marked here. This is Xb gamma in equilibrium with liquid, and this point is Xb liquid in equilibrium with gamma. So, left to Xb liquid gamma will be liquid, and right to Xb gamma liquid would be gamma phase, fine, single phase gamma. So, exactly, and in between these two we have liquid plus gamma phase, of those specific compositions. Fine. So, like that way we can actually have a kind of relative positions of all three free energy composition plots, and corresponding temperature composition plot can be marked there. Now, one more temperature we missed. If I try to two more, if I try to do it, this is G. If I try to do it at T equal to Tm A, we will get a plot like this. This is liquid line, this is G2 delta, this is G2 liquid, and this is G2 gamma, this is G. So, now you will see that when x b equal to 0 or x a equal to 1 pure A, I will have liquid and gamma phase to be coexisting, and this is x b equal to 1, x b varying this way. So, rest of the zone we have only gamma, because gamma has lowest free energy. Okay. And finally, if I go to T 5, I can draw those plots. This one should be marked in red color, because G2 delta, that is always red colored. Is that correct? So, this should be my G2 delta. This is liquid line, liquid free energy, G2 liquid, and final one is G2 gamma. This is G2 gamma. This is T equal to T5, and everything would be gamma. This is XB, composition XB, XB equal to 1, XB equal to 0. This is G. Fine. And you see over the entire composition range, gamma is stable, since it has the lowest free energy. Now, whether this diagram is drawn properly or not, how to judge? As we have seen that we have to see the dotted lines which are reflecting metastable compositions, and those metastable composition, if we had seen in case of eutectic as well as eutectoid, all cases those are actually entering into two phase zone. Let us see that part, whether the phase diagram is drawn correctly or not. In order to judge that, you can take this metastable composition marked in the phase diagram. For example, in case of eutectoid, rather we started with eutectic, x b this way, x b equal to 1, x b equal to 0, and let me just draw the eutectic one first. Let us say this is temperature, this is liquid, S1 plus liquid, S2 plus liquid, this is S2, S1 plus S2. And in case, let us say the two terminal solid solution which are coming out, they have different crystal structures, then we can actually put it as alpha, which is A rich, and this particular thing can be put it as beta, which is B rich. Okay. So, that is the only difference if the crystal structures are different. If crystal structures are same, S1, S2. Now, in this case we see that all those metastable compositions are entering like this. You recall we have done like this metastable composition. Those are basically metastability decided by common tangent again, but that common tangent will be lying above the stable common tangent, okay, or the equilibrium, stable equilibrium common tangent. Now, you see that all those dotted metastable lines are actually entering into two phase zone. Okay. For example, this particular X B S1 S2, that is the composition that is entering into S1 plus liquid zone when we take it metastable, and a similar way you can actually reflect. Now, if this is eutectic phase diagram. Now, of course, these 2 points are TM B and this is TMA. Now, if I look at eutectoid, the pattern would be similar, but liquid would be replaced by another solid. Let us say those solids have different crystal structure, XB equal to 1, XB equal to 0. So, let us say this is beta, this is alpha, as we have seen the notation A reach and B reach, alpha plus gamma, this is gamma plus beta, this is alpha plus beta. And here also if I mark the metastable compositions, those composition again will see that is entering into two phase zone. That is the way to judge. If that happens, then that phase diagram is drawn correctly. Now, the third one is this is eutectoid. The third one is here, which is peritectic. So, we have seen this was the diagram we have drawn. This is XB equal to 1, XB equal to 0, this is TM A, this is TM B, and here you can say TM T transform, which is gamma beta, and here T gamma alpha. These are the equilibrium transformation for the pure metals. Now, this is delta plus liquid, this is delta plus gamma, this is delta, let us say this is liquid plus gamma, this is gamma. Now, if I try to extend the stable composition into metastability, so this is going extended like this. So, this is extended like this, this one is extended like this, this one is extending like this, this one is extending like this. If you do follow this up with the free energy composition diagram, you will get all those dotted lines, those are the metastable lines. Again, you see any dotted line you consider, that is actually entering into two phase zone. For example, if we talk about the composition of delta in equilibrium with gamma, that is entering into delta liquid zone, and whereas if we try to look at composition of liquid in equilibrium with gamma, so that means this line, if I try to see, that line is entering into, again that dotted line is entering into delta plus liquid zone. So, like that way all the time those metastable compositions will actually lie in the two phase zone. Okay. So, that way we can actually judge whether the phase diagram is drawn correctly or not. This is peritectic phase diagram. Now, in case of iron carbon diagram, so we have seen here the only difference here would be if I try to plot the free energy composition diagram at a temperature which is, let us say here. So, that case the free energy composition diagram would just shift. On the right side, this is temperature, this is G, this is the temperature we are talking at T prime, this is weight percent of carbon, and these are the 4 compositions I am talking about. Okay. Those composition, how would that come? I can get the gamma free energy like this side would be liquid, then we have gamma, then we have delta. So, in this case 3 tangents, so 2 tangents we can have, this is one tangent, this is another tangent, these are the compositions, 4 compositions, this is xc of delta, this is G2 delta, this one is G2 gamma, and this one is G2 liquid. So, this is xc, that is carbon of delta in equilibrium with gamma. This is xc of gamma in equilibrium with delta. This is xc of gamma in equilibrium with liquid. This is xc liquid in equilibrium with gamma, and these are the 4 compositions. This is xc of liquid in equilibrium with gamma. This one is xc of gamma in equilibrium with liquid. This one is xc gamma in equilibrium with delta, and this one is xc delta in equilibrium with gamma. Like that way 4 compositions can be marked. Only difference is in case of generalized diagram, what we have considered, we have taken the liquid stability which is little at a lower temperature on the left side, and whereas solid stability is higher B side. But here the plot pattern is little different, just opposite. In case of iron carbon diagram, we have kind of situation like this, what we have drawn in case of G composition plot, and this is pure iron side, and of course, this is some arbitrary compositions we can take, let us say 2% we take, and then this all those free energy lines can be contained within that, and equilibrium conditions are marked like this. Okay. See, here I have put all the composition in terms of mole fraction xc of delta, gamma and liquid. You can actually convert this weight fraction to mole fraction also, fine, in such a fashion that entire all those free energy composition lines will be contained within that range. Okay. So, then you can actually definitely write in terms of mole fractions, and those mole fractions also are placed here. So, you can actually convert to xc in this fashion, fine. So, now you see we have seen eutectic, peritectic, eutectoid phase diagrams, and we try to understand how to get those diagrams with reference to free energy composition plots and equilibrium considerations. So, now we will close today's discussion. Now, the one thing that is left for the discussion, that is phase rule. So, that phase rule we will consider in our next lecture, and that will be the concluding lecture. Okay. So, let me stop here. Thank you very much.